Temperature's effect is as you increase temperature, the rate of reaction increases. First thing we should realize is temperature is average kinetic energy. The higher your temperature, the more kinetic energy you have, therefore, the more movements they bump into each other, and you should have faster reaction. But I'm going to call this a minor effect. So the first one, which is just average kinetic energy increases, is sort of a minor effect on the rate. The major effect that we refer to according to Maxwell-Boltzmann distribution curve is now more particles have energies bigger than activation energy to react. So this is a major effect. And I'm trying to sort of dissect this with you and see if we can understand it. So what I have in this beaker is, imagine there are two red dots, or those that have, so this have energies bigger than activation energy. Total, I have 2, 4, and 3 more. That makes it 9 particles that are in this reaction. 2 have enough energy to react, and then the remainder 4, they have energy but not bigger than activation energy, so their energy is smaller than activation energy. And then finally I have the green ones to also say they have very low energy, which is much smaller than activation energy. Now, Maxwell-Boltzmann, what they want us to realize is we be able to produce this distribution curve. The y-axis simply has number of particles you have as reactant. The x-axis is kinetic energy or movement in kilojoules per mole. So the curve looks like this at a given temperature. You will have a distribution like this. It never meets x-axis, and the area under this curve represents number of particles you have. In this case, I had 9. So some of your particles are here with low energy. Most of your particles are here, but they still don't have enough energy to react. And then you also have few that are here and are going to react. A few that have enough energy to react. Now, if you look at this curve that I produced here, energy diagram, the reactants are down here. In order to make it to activated complex, this is amount of energy, and 60, take away 10, you get 50 kilojoules, so I put 50 kilojoules here. So in this representation, I only have 2 particles that are capable of reacting. Now what happens as you increase the temperature? So the same beaker, temperature is being increased. Imagine this is cold, and let's see what happens when it gets hot. So the red here was the cold. That sort of is representing number of particles you have in the reaction. Only few of them are reacting. Now when you increase the temperature, now more particles are going to have energies bigger than activation energy. In order to show that in your Maxwell-Boltzmann distribution, you have to produce another curve which has its height should be lower than the one before, and it should spread further to the right. So we have the same number of particles, and I'm going to slightly spread to the right hand side. Now what happens here, this represents that we have more particles that have energies bigger than or equal to activation energy. So this one in a blue greenish is trying to say the hot beaker compares to a cold beaker. And when you do that, more particles we will have energy sufficient, bigger than or equal than activation energy to react. And your activation energy didn't change. Now the question is, what happens if I introduce a catalyst? If you introduce a catalyst, what you're going to do is lower this activation energy. So even for hot and cold, now you will have proportionally more reactants that can react. So this, let it be, the new blue line is EA with catalyst. So temperature is very important factor. You increase that, the rate goes up. There is a minor effect. Particles will have just simply more movement or kinetic energy. They react faster. The major effect is now more particles in that given volume will have sufficient energy to react. They can go over this hump and react.